is Melissa Graham, and she will talk about the ZTF transient classifications with DIS.
Wonderful, thanks. Hello, everyone. My name is Melissa. I'm at the University of Washington, and I've been using APO for the last couple of years with DIS to spectroscopically follow up transients from this wiki transient facility from ZTF. And I just want to note the large number of observers and collaborators that have contributed to this program over the last couple of years. So I want to start, even though we just had a talk about supernovae, I wanted to start with what's a transient, because I know that not everyone knows the lingo. And so a transient is just any limited time, non-recurrent change in an object's brightness. And the class of transients includes stellar explosions, eruptions, and collapses. So things like novae, kilonovae, and supernovae, and also things like tidal disruption flares when supermassive black holes basically eat a star and the emission that comes from that. This is just an example of how we find transients, the new point source that appears usually near a galaxy. In this example of the detection triplet of the new, the old, and the subtraction images from ZTF. So that's what a transient is and how we find them. But you did just see a bunch of really nice examples of light curves of supernovae. And sometimes the light curve is enough to classify it, but really you want a spectrum to spectroscopically classify the type of transient that you're seeing. And so these are just examples of supernova spectra, where we use the spectral features that we see in the optical spectrum to classify the supernova type. So you've got your usual, kind of the usual suspects here of the three main kinds of supernovae, the type 1As, the type 1C and 1Bs, and the type 2s, where the 1As show a lot of silicon and they don't show any hydrogen and helium, and they come from thermonuclear explosions of carbon, oxygen, white dwarf stars, whereas the 1Cs and 1Bs are the core collapse of very massive stars that have lost a lot of their hydrogen and helium due to winds. And then the type 2s are core collapses of about 8 to 25 solar mass stars, and you see like the classic hydrogen profile there in their spectrum. So that's what a transient is. These are some of the typical supernova classifications, and this is why we need spectra in order to classify them. And now I want to say just a bit about the ZTF Bright Transient Survey, the BTS. So ZTF itself is a mix of public and partnership surveys. And the BTS, the Bright Transient Survey, uses just the public images and public transients. The goal of BTS is to obtain spectra for all transients that peak brighter than 18.5 magnitudes. And so the strategy for going about doing that is to actually try to follow up all of the transients that seem like they're going to peak at above a magnitude of 19 in brightness, so that you're inevitably going to be incomplete at your lower limit. And so so the idea is that you'll be complete in your spectroscopic classifications for brightnesses less than 18.5. The strategy to achieve this is to have a wide variety of resources at your disposal to do your spectroscopic follow-up. The powerhouse one is the SED machine that's also at Palomar, which is where this Wiki Transient Facility survey is being run from. There's also just a variety of collaborators that contribute mid-sized facilities to the spectroscopic follow-up effort. I'm one of them with APO, and the team at UW is doing that with APO. And then there are team members who also have Gemini and Keck to sort of clean up anything that has faded too far for the mid-sized facilities to really make sure you're getting that 100% spectroscopic completeness for your sample. The entire BTS dataset is pretty much public, so I put the link here in case you're interested in perusing what they've got and looking at their page. This is just a screenshot from the main BTS page that gives you an idea of the kind of information that they've made public for people. And then I just wanted to point out that the team leadership for BTS is really being spearheaded by Christopher Fremling, Dan Purley, Adam Miller, Ariel Gubar, and others. They're really sort of leading the way with this. So for the BTS, like, why would you want to do this? Why do you want to build a spectroscopically complete data set of bright things? This is an example of sort of 4 of the main science areas where you can make significant advances when you do a survey like this. One of them is redshift completeness studies. So that's when you're looking at the fraction of all supernovae that you detect that are in a host galaxy that already have a redshift, and understanding what that number is and why it is and how it changes with redshift is really important for the future of gravitational wave follow-up and the future kind of follow-up studies where you're looking to do things really rapidly, like we just heard about. So knowing what information you already have on hand can change your strategy in cases like that. The other main science goal for BTS is transient occurrence rates and progenitor populations, which obviously you can only do really well with a very complete sample of spectroscopically classified objects. You can also use this sample to build machine learning training sets. So you just saw examples of nice light curves. In the future, you definitely won't be able to get spectra for like every single LSSD transient, for example. So having a good connection between light curve shape and spectroscopic classification is necessary in order to use machine learning to do your classifications in the future. And then of course, sort of the fun science output from this is you get to characterize all the weird and rare transients that show up in this very complete sample. Like when you're not just looking for 1As, you start to find all the weird stuff and you can do science with them as well. So this is just an example of a bunch of papers that people have been looking at individual objects that are interesting in some way. And I will note overall that I think the only paper on this list that APO didn't contribute to directly is the machine learning training sets one, but of course it contributed indirectly by providing public classifications for that work. So how exactly does APO fit in with this effort? In 2018, we started working with the first ZTF survey, ZTF1. We were doing about 6 half nights per quarter, following things up on a classical schedule. We had a mix of A and B halves, and we always do just low resolution spectroscopy, just trying to be as efficient as possible with our time. For ZTF2, which started in 2020, we dropped down to 3 A halves per quarter. We started realizing that APO, because it could go fainter than the powerhouse ZTF machine or SED machine that was doing a lot of the follow-ups, we really wanted to focus on using APO to classify objects that were old, they're fading, they're starting to set. It's like a last chance kind of thing. So we started focusing on just doing A halves and following up those essential targets and trying to make like the best contribution to the science that we can with APO. Over the last couple of years since 2018, we've obtained about 100, more than 100 now, new classifications and 100 monitoring spectra of transients from the ZTF. Overall, we've managed to contribute data to 12 publications and many, many more telegrams, which are basically little unrefereed publications that are how the time domain community communicates with each other about spectroscopic classifications. And we've used this long-term program to train and provide experience for new observers as well. So down at the bottom here, you can see our team on our training run back in 2017. And then on the right here is a pie chart of our classifications of ZTF supernovae by type, where the type 1As, they're the brightest. So they're the most common ones that show up in a data set like this. And also they're really easy to classify because of just the way their spectrum is shaped. It's pretty unambiguous, you know, when you found a 1A. So that's making up the most of our supernova there. And then we've got type 2s, type 2Ns, which are ones that have narrow lines, which is another sort of niche scientific contribution of APO. We're doing low resolution spectra in terms of like which disk ratings we use, but it's still much higher than SED machine. And so there are some kinds of supernovae you can only classify if you see the narrow lines. And so I do try to target those as well with APO when it's something that looks like maybe you need a higher resolution spectrum to classify. We'll prioritize that in our APO program. And you can see that it's been working here with that orange wedge of a lot of narrow line supernova being classified. In the future, we want to think about how we continue to evolve our use of APO to keep it efficient and keep it contributing as well as possible. So our current target selection strategy is very human run, very intensive. The human, me, I select and I prioritize unclassified BTF transients for DIS. I'm thinking about which objects most need classification, which objects DIS would like really excel at, where can we really provide, like get the most bang for our buck basically. And then the human observes and processes the data and distributes the results. And the human / an algorithm sometimes combine to recognize the spectral features and classify the targets. But things are changing in the time domain field. We can't be spending so much human time on all of these aspects of our follow-up anymore. So people are now developing algorithms to both select and prioritize targets for spectroscopy. So we could start doing that also for BTS or from any survey really, and use them for DIS. Still we'll be doing a lot of human observing with DIS because there's no plans to roboticize, obviously, and that's fine. So the human will keep observing with DIS. But then we could also be making better use of algorithms to process the data and classify our targets. And so thinking about the future, those are the areas where I want to make changes and move forward with this program in. And right now I'm considering sort of a ZTF. I mean, I don't think it really plans on ending, but I am considering joining teams who are working on developing this kind of software infrastructure in the field, and to do like a little more, to have a little bit more help with some automated target management and make further, better use of APO in the future for the time domain. The other thing I wanted to mention is that having APO access enables other research opportunities as well. So beyond the direct contribution of DIS data to like other people's publications, just having APO access and being able to contribute that data to ZTF has really been a foot in the door to the ZTF collaborations and working groups. It's something I can take and say, I can observe with APO, can I join your collaboration? And they'll say, yes, would you like to write a paper using our data? And I'll say, yes, please, that sounds like fun. And so by participating in BTS, I was able to take on a ZTF data, which is directly relevant to the end of the last talk as well. This paper is all about supernova siblings and their parent galaxies from the ZTF. And this is a paper that was really fun to write with a lot of other people in the ZTF, and it's a paper that's currently in review. So APO has just been a great thing for me to have and use, and for all the folks at UW as well. So I just wanted to thank you very much for listening and leave you with some of these nice pictures, which are relevant to all our interests. Yeah, thank you.
Thanks, Melissa. Any questions from the audience? I'll ask one. Well, okay. Well, let's go with Nancy first. Go ahead, Nancy.
Thanks, Melissa. That was great. I guess my question is, are there things in terms of how the telescope gets scheduled that would that you would want to see done differently in order to optimize the success for your observations?
Yeah, so right now classical time is kind of working for us because of the way a BTS is run, because there's always lots of targets, so there's always lots to choose from. If we were trying to participate in something else that didn't have so many targets all the time, then we'd be doing target of opportunity, but I think you're going to hear all about that from Eric coming up next. And so from there, I mean, you either have your classical TOO mix or you do something like Q. And Q is always better for time domain studies because you can get your stuff in sort of whenever you want and whenever it's best to make that observation. So a lot of these software infrastructure tools I was talking about that do your target prioritization for you, they'll tell you what's important at any given time, or they'll say, oh, this object is like rising in this way, you should get a spectrum in 3 days or in 2 weeks. And so you can, if you have Q, you can plan and you can use it that way as well. So, I mean, Q would always help, but I know it's expensive and hard. So yeah.
So MDM and Osmos has a Q program as well. I don't know if there was any discussion of starting a Q with Cosmos maybe when it's available.
I have not heard.
If that's a question for me, I can, not yet. We haven't formally talked about that, but I think that, part of what I'm trying to do with this meeting is to gauge where people's interests are and see, how we might plan for the future.
Right. Cool. All right. Any other questions? If not, thanks, Melissa, again. And let's move on to the next talk by Eric Belm.